The analysis in the previous lecture brought out several interesting points. One of the things we considered was we decided on one particular form of the input, that is e raised to st plus alpha, and this input was very special in the sense that if you give this input to a linear circuit, that is has inductors and capacitors and resistors, all components in which these values are constant and not dependent on the current itself. So, you have got linear inductors which are denoted by their behavior is obtained from voltage across it is equal to L di by dt, where L is a constant, and similarly the current through a capacitor is C dV by dt, where C is a constant and R is also a constant, not dependent on the current or voltages. So, this kind of circuit, which is a linear one, has an interesting property that if you apply an input e raised to st plus alpha, you find that the response is in steady state has the same wave shape. That is, if you have e raised to st plus alpha as an input to the system, then you will find that the output in steady state also has the form e raised to st plus alpha, but there is of course a scaling factor, and there could be that scaling factor in fact for conditions where S is complex, that is when you have sinusoidal inputs, you will find that in fact there is a phase shift as well. So, there will be a scaling and phase shift, or rather in other words the scaling itself is obtained by putting S is equal to j omega. So, what we saw was that in case you have got a system which is linear, it is a linear circuit of lumped elements, which is in fact described by a set of differential equations, and you apply an input u and you take a measurement y. It could be anything, it could be for example in the RL circuit current through the inductor. In that case you will have in case u is equal to e raised to st plus alpha, your output in steady state is also e raised to st plus alpha divided by a scaling factor, which is essentially a a function of S. So, this is what we saw. Just to give a simple example rather than talk in abstraction, if you got an RL circuit and the input is voltage and the current measured through the inductor is the current, we saw that if your input is st plus alpha, then the current turns out to be e raised to st plus alpha, the same wave shape, but divided by R plus SL. Interestingly, so when we look at an RLC circuit, what we saw was a simple series RLC circuit, R SL 1 upon SC. So, what we saw was if your voltage was V of t, then the current would come out to be, if this was the voltage, the same wave shape, in that case the current turned out to be e raised to st plus alpha upon R plus SL plus 1 upon SC. And interestingly enough, the DC situation is obtained by putting S is equal to 0, and if you want to look at an AC, that is if you want to look at one sinusoid, then you plug in S is equal to j omega. The important thing to note is this is only the steady state behavior. In fact, in transients what we notice is that very interestingly is that the roots of this polynomial which come which are obtained by setting in the case of an RL circuit R plus SL is equal to 0, or in the case of the RLC circuit this is equal to 0, roots of it that is in this case S is equal to minus L by R, I will call this S1, and here S1 and S2 is equal to, you will get lambda sigma plus or minus j omega n. These are in fact also interestingly the nature of these in fact indicate the nature of transients you will see. So, interestingly enough, this analysis reveals not only how the behavior in steady state would be, but also what the transient the terms in the transient behavior will be. For example, this essentially reveals that have I got this right? No, I have got it wrong. It should be R by L. The transient, the roots of R plus SL, which is in fact the denominator here. Okay. So, you have to define an input and an output, in this case the current and the voltage, and based on this you can get transfer. This is also called this 1 plus RL 1 upon R plus SL is also called the transfer function. This reveals the nature of terms in the transient behavior. So, you will in fact in the transient behavior see this in your response, these terms, whereas here you will get sigma plus j omega n and e raised to sigma minus j omega n. And since we know that a combination of these terms can yield sinusoids, damped sinusoids, these terms, you know that this essentially leads to a decaying oscillation. Of course, that depends on the value of sigma. If sigma is not too large, then you will have an undamped oscillation like this in the natural response. So, remember one thing of course is that circuits of this kind have a natural response, which generally with, since the resistances are positive, you will find that they die out with time. What remains is of course the steady state response, which is given by this. In fact, since we know that sin omega t can be written in terms of e raised to j omega t and e raised to minus j omega t, an interesting thing is just by plugging in s is equal to j omega, you can in fact get the information of what would happen when you have an input not e raised to st plus alpha plus sin omega t plus alpha. So, if you want to know what happens when you put sin omega t plus alpha, all you have to do is plug in s is equal to j omega, and what you will find that in that case this will be effectively 1 upon R plus SL will effectively become square root of R square plus omega square L square, and you will get this phi, where phi is equal to tan inverse omega L by R. Similarly, this you can plug in s is equal to j omega and also similarly get a magnitude scaling and a phase scaling. Okay. In this case, of course, very straightforward for a RL circuit. As the circuit becomes more complicated, you will find that this it is easiest to simply take a circuit and wherever there are capacitors you replace them by 1 upon SC, and wherever there are inductors you replace them by SL, and try to get the transfer what I call the transfer function, and also understand what kind of terms you can see in the response. So, one more circuit we saw last time was in fact a circuit of this kind. I think the inductor on the other side, but it does not matter. So, this is L1 and this is L2 and this is C and R. So, in case you wanted to, for example, if you are trying to look at the input as V, the voltage, and the current as or rather the output as V naught, in that case you can easily replace this circuit as I mentioned some time ago by SL 1 and C 1 upon SC, and this becomes SL 2, and get the what is known as the transfer function between V input and V output. So, this is quite easy to do. In fact, this is a parallel combination of SL2 and SC, and this is in series with this. So, you can in fact get the current flowing through this, and once you get the current flowing through this, you can in fact infer what is the voltage across this. So, what can you do in this circuit? There are two things you will find, that the steady state can be obtained by the method I told you. You can actually get V naught by V1, which is nothing but okay, let us work it out. So, you will find that V naught t is equal to the current in fact, if you look at this, this is a parallel combination of SC and SL2. So, let us just do that. So, you got R, we will do it a bit fast, L1. Of course, the problem in doing it fast is this element here is a parallel combination of 1 by SC and SL. So, it is SL2 upon 1 plus SL2 divided by SC. So, this is what is the parallel combination. So, you will get V1 of t. So, V1 of t, of course, if it is an input, we assume that it is an input e raised to st, and then what you do is R plus SL1 plus 1 upon SC SL2 upon 1 plus SL2 by SC divided by, let us say this is, in fact, you can multiply this by a constant as well, which I did not actually show you here, but that is also possible. So, this is what you actually see in this circuit, and as I mentioned some time back, the nature of the transient response can be obtained by simply setting this denominator term of this, what I call this transfer function 1 upon this to be equal to 0. So, a minor error here which has been which has crept in, this should be not this should be not this, but the denominator should be S1 upon SC plus SL2. So, this is 1 upon SC plus SL2. So, this is what we see as the this we call in fact as the overall impedance of the circuit, and this is a function of S, and of course, if we set this to 0, the polynomial which results which we in fact will yield in fact 3 solutions. So, in fact, you will find that S, this will be a third order polynomial, is something which you can verify. Since it is a third order polynomial, you will find that there are 3 roots of S, and your natural response will consist of in fact terms for the values which are depends on the values of R, L and C, and in case R is small, you will find that this will certainly have one pair of eigenvalues which is complex, and therefore, you will have terms of e raised to terms like e raised to sigma plus j omega t and e raised to sigma minus j omega t. Remember, a polynomial with real coefficients, whenever you try to take out the roots, even if you get complex numbers as roots at times, they will always appear as complex conjugate pairs. So, what you really will have is if R is small, it is not you can really show that you will have one real root which has got a negative real part, and one complex root which again has a negative real part, and so you will in fact have a oscillatory behavior as well as a exponentially decaying kind of behavior in the natural response. The steady state response is obtained simply by putting an appropriate value of S in this equation. Okay. So, this is what to summarize, you got a natural response and a steady state response in linear circuits. The steady state response has the same wave shape as the input waveform. If it is of the form e raised to st, we can represent sinusoids as also as e raised to st, because you can plug in S is equal to j omega. Remember that linear circuits also satisfy an important property called superposition, in the sense that if you have got an input with 2 frequencies, you can actually get the steady state response for this composite input of 2 frequencies by actually getting the steady state response for each of them separately. Okay. The natural response of course is dependent on the roots of the so called characteristic polynomial. In fact, in this case the character if you look at this SC R, SL, 1 upon SC and SL2 are also called the impedances of these elements. Okay. The reciprocal of impedance is also called admittance. Remember that you can use this SL and SC in much the same way as you use R in a circuit. So, it becomes easy to actually do this kind of analysis for certain kinds of inputs. So, if you have got inputs of e raised to st, things are very straightforward. So, remember there is a natural response. The natural response what is the natural response? Actually, the natural response will contain terms with e raised to lambda t, where lambda are the roots of that characteristic polynomial. But what we have not of course discussed what should be the magnitude of the natural transient. The natural transient actually depends on two things. One is the initial condition on various elements, and the second thing is of course the instant at which this source is switched on. So, it really depends on the nature of the input as well as the initial conditions of the elements. Now, when I say initial conditions, why are they important? Because when you integrate a differential equation, what is important is what is the value of that, for example, if you got an inductor and if I tell you the voltage across is Vt and I tell you find out I of t, you will do I of t is equal to 1 upon L, you have got in fact, sorry, let us just do it properly, L di by dt is equal to V. So, di is equal to V by L dt, and when you integrate it 0 to I di, I is the instantaneous value of at time t, and you will get V, suppose this V of t is, so you will get 0 to t V of by L into dt. Let us say V is suppose if you look at this, you will find that I of t minus I 0 is equal to integral 0 to t V by L dt. So, what you find is I of t is not only a function of what V is, but also is a function of the initial condition. In fact, all elements which are described by some differential equations like capacitors and inductors are likely to have you need to specify the initial values also in order to understand how they will behave. In the RL circuit, you need to know the initial value of the current, and you will notice that the natural response also depends on the initial values. So, that is very important. Of course, there are some interesting side effects which you should remember, that is it true that all the capacitors and inductors, their initial conditions need to be specified? The answer is of course, one has to be look at this a bit carefully. The initial conditions in fact have to be given under very specific circumstances. For example, if you got two inductors in series, okay, they may be physically two different inductors, but if they are in series, the current through them has to be equal. So, you cannot specify the initial condition of these two inductors independent of each other. Similar thing happens when in your case you got say a all capacitor loop. The voltages on all these capacitors cannot be specified independently, because your if you apply KVL, then they in fact there is a constraint that the sum of the voltage drop should be equal to 0. So, it is not true that all capacitors and inductors in a circuit, their initial conditions can be given independently, at least in ideal circuits. Of course, you may argue that in real life there is no problem in doing that, because actually there is, as soon as you make a loop, there is a change in B which may occur as soon as the current flows, and because of that you will have a voltage drop in this loop by Faraday's law, which is dependent on the rate of change of current, because the current causes B, the rate of change of B will cause E dot dl to be non-zero when you integrate over this loop. So, in some sense this non-ideality saves us if you actually give independent initial conditions. But if you assume this is an ideal circuit with no loop inductance, which is actually not true, you will find that giving independent inconsistent initial conditions to these three capacitors will land you in a soup. I mean, you will come across for example, if this is 5 volts, this is 10 volts and this is 3 volts, you end up with the inconsistency, it does not follow KVL. Okay. So, this is a kind of prohibited, but in real life if you do this, luckily there are a lot of non-idealities, like as I mentioned, the loop inductance, the resistance of the wires and so on. So, that will save you in some ways. An interesting thing of course is if you have got a circuit like this, it is easy to choose the states, because here in fact you can the inductor current and the capacitor voltage are independent states. You can I have used the word states, or rather I should say that I can independently specify initial conditions here, whereas here you cannot. Again, in real life you may be saved by the fact that any metallic wire, if some charge buildup occurs, then there is an electrical field and there will be a voltage drop. So, in some sense any metal separated by a dielectric or insulating material would in fact have a bit of a stray capacitance, and that would really save us. In this case you could actually specify these currents independently. So, there is an issue of this needs to be carefully looked at. If you consider ideal circuits, there are some constraints of how you can specify the initial conditions. Okay. So, but if you take real life situations, you normally see that some non-ideality helps you in avoiding such a situation. Now, so in fact, I use the word state without actually defining it. So, what you notice is that in all circuits, the KVL, KCL equations and the initial conditions will allow you to predict how the circuit behaves in future. You can solve the circuit either analytically or through a numerical integration program. The minimum in some ways information you require is the input and output and some initial conditions. Okay. So, in fact, therefore, this concept of a state comes. If I, for example, in this circuit tell you what the initial conditions on L and C are and also specify the inputs, you should be able to specify how this is going to behave in future. You do not require only two initial conditions, one for the inductor and the capacitor. In the unusual case where you got two inductors, you in fact cannot independently specify two ideal inductors with no parasitics between them. You cannot in fact specify the currents independent of each other. So, there is only one state here, even though you may have physically two inductors. So, if you neglect parasitics here, in fact you have got only one state, and in fact this is also an important thing, because although I have in the circuits I have shown you, I have defined what my input is and an output is. For example, some of the things which are proscribed would mean that it is not allowed, is that if you have got a current, if you are specifying a current through an inductor like this is generally not allowed. The reason is that you can allow it provided this current is absolutely consistent with this initial condition. Okay. So, if you are for example, another example is a voltage source being connected across a capacitor. Now, if the initial condition is this 5 volts and this is 5 volts, you will not be violating KVL, but in case this is 5 volts and this is 3 volts or 0 volts, you connect this, your voltage across the capacitor is 5 volts, but I mentioned some time ago, in case the voltage jumps to 5 volts, dV by dt becomes infinity, and therefore, the current will have a infinite kind of spike. In fact, it will be an impulse kind of current. So, you will have infinities, mathematical incongruities which will occur. So, normally this kind of circuit is not allowed. In fact, in real life, as I mentioned, the parasitics save us from having infinities, because you know that there are resistances here and the loop inductance is here. So, you will not have in fact KVL violated in real life, but you will still have an extremely high current, because these inductances and resistances or the parasitics are extremely small. Okay. So, in fact, remember that we need to consider the choice of what you connect across a device has to be done carefully. In case we have situations where you may have problems, for example, you are having an inductive current flowing in a circuit and you want to interrupt it. Suppose you have got this circuit and you switch this on, you switch it on, the initial condition on this inductor is 0 and the current when you switch it on also the current is 0, but suppose you reach steady state, then the current in steady state is V by R. So, if your current is V by R in steady state and you want to now open the close switch, in that case you have a problem, because if this switch opens instantaneously, the current will have to go to 0 instantaneously, and that really creates a problem, because of the fact that this inductor current can't go suddenly to 0, because the di by dt would be infinity. So, the voltage across the inductor would be infinity, but again the non-idealities save us, because when you actually try to interrupt this current, the voltage starts reducing, and in fact when you open the switch an arc is formed. So, it is not actually current really does not interrupt instantaneously. So, the high voltage which appears because the current starts dropping as you open the switch creates an extremely high voltage across the switch, which actually breaks down the medium, the insulating medium between the switch contacts, and that has an arc. So, the current actually does not extinguish instantaneously. So, that is an interesting point which from the point of view of in fact design of switches, that you can actually have this problem of a spark in a switch. Why does it occur? In fact, it saves us because otherwise you would have infinite voltage and the whole thing would explode. But because as you open the switch contacts, the current tends to fall, the current does not go down to 0 because when the switch are just sparking, there is enough voltage between the switch to allow certain current to flow between the switch contacts, and that current does not extinguish to 0 instantaneously. So, this is an important point which you should remember. One aspect which I mentioned in passing some time ago was, let us just summarize. You have got a transient behavior and a steady state behavior. The steady state behavior has got the same wave shape as the input if the input is of the kind e raised to st. You can in fact allow for sinusoids, exponentially decaying inputs or DC by putting appropriate values of s, and you also have a natural transient. The natural transient usually dies down with time, especially in circuits where there are positive values of resistances, and what remains is the steady state after a long time. The transient behavior or in fact adjusts itself in a way so that the initial conditions are satisfied. So, this is a kind of overview of what we have already done, but I thought I will just repeat it in several times so that it is absolutely clear. Now, one of the important points is of course of what happens in case you do not have one input, but for example, you have got an input of various frequencies. E raised to st plus alpha I said was a generic input, but what if I have for example, sine omega 1 t a1 plus a2 sine omega 2 t. I mentioned some time back, if you got two inputs, then the sinusoidal steady state real behavior will also consist of omega 1 and omega 2 frequencies. That is, you will have an output omega 1 t plus alpha 1 plus depends on the circuit, you will get the response to be B1 and B2. The responses also will have these terms. The wave shape kind of is of the individual sinusoids is preserved, but the scaling factors and phase shifts will depend on the evaluation of for example, in an RL circuit evaluating R plus SL at those two frequencies. So, your responses are in fact a superposition. In fact, in nonlinear circuits, if you excite it with sin omega t, you may get, even though you may reach a sinusoidal steady state, even if you excite it with one frequency, in the periodic steady state you may find 2 or 3 frequencies or more. So, that is an interesting about nonlinear circuits, but for linear circuits there is a causal relationship between this and this and this and this. So, in fact, you can get what is known as the frequency response quite easily of the circuit. Now, what is the frequency response? Frequency response is the sinusoidal steady state behavior if you evaluate it at various frequencies. For example, 1 plus R plus SL, if you take this as a transfer function or the factor which is multiplying the input and out, if you multiply this to the input which is of this form, then the output will be 1 plus R plus SL in that RL circuit. The current will be 1 by R plus SL into e raised to st plus alpha. So, this factor which actually tells you the scaling and possibly the phase shift in case it is a sinusoid in the sinusoidal steady state will can actually be represented by a frequency response. That is, what do I mean by that? By plugging in values of s, you can actually get, for different values of s, you can actually get, for example, s is equal to j omega, that is I evaluate it for sinusoids or cosinusoids. So, if I apply j omega, you will apply S is equal to j omega, you can actually take out the magnitude and the gain. So, this is the magnitude of this and the gain. It is very easy to see that when S is equal to 0, the magnitude will be 1, because S is equal 1 upon R, because S is equal to 0 gives you 1 upon R. But in case of course, you put larger and larger frequencies, the denominator magnitude increases. So, you will find that R square plus omega square is the magnitude, and if you plot this, you will get a curve of this kind. Okay, okay, that's fine. And the phase in fact is what you, if you plug in S is equal to j omega, what you will get is at 0 frequency, this is 1 by RL has 0 phase, but as S increases, you will go to minus 90. So, what I call is 1 upon R plus SL's angle goes to minus 90, because for example, S is very large, this term will predominate, you will get 1 upon j omega L. So, this is minus 90. So, this kind of curve is called a frequency response. What it really denotes, so any point here denotes the magnitude scaling which you will get if in sinusoidal steady state, if you have got an input at that frequency. If you have got inputs at 2 frequencies, you can of course get it from this curve, the input and the output. Actually, something I will not prove here is that it is convenient to plot this magnitude plot on a log scale. That is, you do not plot it on a linear scale, but a log scale, because this slope and this slope, as in the log scale, that is the x axis, both the frequency and gain are plotted on a log scale, you will find that. So, if the gain, that is 1 upon R plus j omega L, that is the gain, if you plot this, you can show that this is quite easy to show. As omega becomes larger, this actually has got a slope of minus 20. This is called a decibel gain. So, this will become minus 20 decibel per decade. So, if you look at the decibel gain versus log of omega, you will find it actually becomes a kind of a constant relationship, and it has a gain of slope of minus 20. So, instead of plotting just the gain versus omega, you can plot the decibel gain versus the logarithm to the base 10 of omega, and that really gives you this, I will call it the base 10. This gives you a constant slope later. So, it is very convenient to do this on the log scale. Okay? Yeah. So, in fact, you can actually get the sinusoidal steady state behavior of circuits quite easily by doing this. So, what we will really look at in this next few slides is in fact the typical steady state gains and phase shifts which you get, and if you plot it for various frequencies, this is what you get. So, if you look at in fact this RL circuit with R is equal to 10, and you in fact actually here what you do is the transfer function actually is between not the current, I will just mention this here, what is being plotted here is what I am showing you here is in an RL circuit, the input is of course chosen to be V in, and the output is in fact the voltage across this resistor. The voltage across this resistor is R into the current through it, and I of t is equal to e raised to st plus alpha, where this is the input, divided by R plus SL. So, in case you want to find Ri, it will be R upon R plus SL into the input. So, if in fact, so the so called transfer function, this I will call as VR. So, the transfer function VR is equal to R upon R plus SL, or in other words it is 1 upon 1 plus SL by R. Of course, this is into the input voltage, this is the assuming that the wave shape is of course e raised to st plus alpha. Okay. So, it is now if I plug in s is equal to j omega, it will in fact give you this frequency response. So, what I am going to show you here is in fact that. So, this is the voltage VR, the what is being measured is the voltage across the resistor. So, in fact, the transfer function has a gain of 1 because the transfer function becomes R by R at 0 frequency. So, if in decibels this will be log 10 of 1. So, 20 log 10 of 1 which is actually 0 decibel, and then it drops down. So, actually you will notice that this is also what is known as a low pass filter characteristic, because it allows it has almost gain of 1 at low frequencies, but as the frequency increases this goes down. So, in fact, if I give a high frequency input to this this RL circuit, you will find that at your higher frequencies the gain is very low. So, you can actually attenuate higher frequencies using this. Of course, the frequencies at which the attenuation takes place and the amount of attenuation depends on the value of this L by R. So, in fact, for R is equal to 10, if I take L is equal to 1 millihenry, 0.1 millihenry and 0.01 millihenry, you will notice that the curves are different, although the wave shape remains more or less the same. The cutoff, you can say the cutoff frequency at which it starts dropping down is different. In fact, it is useful to define something called a bandwidth. One of the ways you can define a bandwidth in a low pass filter, a bandwidth is defined as can be defined. The most common definition is, so if I am plotting this on the log scale, what you can do is the 3 decibel gain you can look at, and this is called the bandwidth. 3 decibels of course corresponds to a gain of 1 by root 2. So, you can say often it is called a half power gain. Why this is half power is something we will understand when we go to AC circuits, simple AC circuits. So, what you find is this 3 decibel dB gain, this actually is called is one definition of a bandwidth for in a low pass filter. So, what you notice is that in case you have got L by R, which is also in fact the time constant of the natural transient in this circuit. In fact, this is 1 upon 1 plus S by L by R. L by R, if you recall, is the reciprocal of R by L, which appears in that e raised to minus R by L in the transient response. So, interestingly, if your time constant of the circuit is larger, you have got a lower bandwidth. Okay. So, if you got a lower bandwidth means that you will pass through frequencies, low frequencies, but you will very early on you will kind of cut off the frequencies higher than this. So, if your bandwidth is lower, that means you are more responsive for lower frequencies, but you kind of cut off the higher frequencies quite well. So, this is an interesting point which you should remember. So, in the context of filtering, of course, this has to be remembered. Okay. So, we are back to the plot here. So, this is essentially what we get when we try to get a transfer function between a certain input and an output. Yeah. Next. If you look at a transfer function which is different, and we again out here, remember what we are going to do is take out the transfer function between the output voltage and the input voltage. Remember, of course, in our circuits we have been in some ways biased towards so far getting what is known as the transfer function between current and the input voltage. This is also called the impedance transfer function, but you can have other combinations depending on the nature of the circuit. You could have an input as a current source, but remember current source cannot be in series with the inductance. You could have a circuit in which the input is a current source and you are actually obtain the voltage across some point. That is actually called the admittance. Okay. Now, so if you are getting a voltage, the denominator of the transfer function between the voltage and current is also called admittance. The denominator of the transfer function between voltage at some part of the circuit and a current input is called admittance. Okay. If you are measuring the current and the voltage is right at the input, they are also called the driving point transfer functions. Okay. So, this is something which you should remember. This, in case you take a circuit which is slightly different, this is a circuit, you can easily show that the transfer function in fact comes out to be interesting looking circuit, and that is so the circuit is in fact let me just have a look at it from the screen. Yeah. So, this and this. So, if you in fact try to take out this transfer function, it comes out to be 1 upon SC here. So, you will get, and this is R1. So, the transfer function between voltage input and voltage output is going to be, it is quite easy to evaluate this, it will be R1 plus R2 in parallel with SC. So, it will be 1 upon SC plus R2. So, this will in fact come out to be R1 upon R1 by SC plus R1 R2, just one second, this is R1 R2 plus R2 by SC, and this of course this SC can be taken on the top. Oops, I think I made a mistake here. Yeah, this goes on the top. So, this is essentially what we get. You will find that this has got a transfer function which is looks like R1 R2 SC plus 1, that SC will get cancelled off, and you will get R1 plus R2 plus R1 R2 SC. I hope this is okay, which you can just verify this that it indeed comes this way. In fact, one of the things you can see is that this S, in case S is large, this in fact becomes a short circuit. In that case, Vi will become equal to Vr. Does that happen? Let us just check. If S is very large, then this will dominate, and then the gain will become 1. So, it is correct. So, if SC is very large, that is what I was just trying to say. If S is tending to infinity, you will find that this practically becomes a short, because this is a very low impedance, and this becomes, the circuit practically becomes like this. So, input becomes equal to output. If I put limit S tending to infinity here also, you will find that this term will predominate, and for all practical purposes this will be controlled. So, it is correct. So, the transfer function is in fact probably, I hope I have not made any other mistake, SC upon R1 plus R2 plus R1 R2 SC. And of course, if you put S is equal to 0, your you will find that in fact there is one R1 also at the, sorry, yeah, this should be R1. R1, yeah, sorry. So, I have got it right now, I think. So, this is the transfer function between Vr and V input, and you will notice that this is of the form, you will find that it is of the form A plus St 1 upon B plus St2, and if you look at the behavior of this circuit, it in fact is actually having, this is also called a lead circuit. The lead circuit, because it gives a phase shift, a positive phase shift in this circuit, which is in fact you may require it in certain situations, and this has a gain of it depends on the value of R1, and in fact it is the gain of half at low frequencies, which of course has to be converted to decibel, and it has got a high frequency gain of 1. So, it actually becomes 0 decibel in steady state, rather at high frequencies, I am sorry. So, what you get is in fact a lead, this is called a lead transfer function. In fact, if you can also make a lag transfer function, which you can try to play around with this circuits R, L and C and try to get a lag transfer function. In fact, these circuits or filters which I have shown you, we also call these filters, but this is called a lead circuit specifically. This kind of circuit in fact is, they use it for signal conditioning. For example, if you want to give a phase lead of a certain value, say 20 degrees here at this frequency, then you can of course choose values of R1, R2 and C, so that you get this lead at that frequency. So, what you need to do is of course tweak around with these values of R1, R2 and C, so that you can in fact shift the frequency in which you get this lead. Okay. And the amount of lead also depends on R1, R2, R3. So, you have got actually 3 degrees of freedom here, R1, R2 and C, and by playing around with R1, R2 and C, there are 3 things you can do. One is you can decide how much phase shift you want, what frequency you want this phase shift, and what is the steady state gain. Steady state gain, the steady state gain is the low frequency gain here. The low frequency gain is also called a DC gain. So, you can specify the DC gain, you can specify the phase shift and what frequency you want it. So, there are 3 things you specify, you have got 3 variables, you can actually uniquely get the combination of R1, R2 and C to achieve this. Of course, one of the important things when you come to circuits of this kind is that this is a kind of filter or a circuit which emulates a certain transfer function, and one of the important things is this is also called a passive filter. The circuits of these kinds are called passive filters. They may be used in signal conditioning, as we shall see later on in electrical supply systems, to remove harmonics and so on. Okay. How this is actually done is something I will try to tell you a bit later. Not this circuit is a lead circuit, but the previous one, for example, is a low pass filter. This in fact can be used as a filter in signal conditioning circuits, or it can be used in even in power circuits, okay, to do filtering, to remove high frequency components. One of the important things of course which you should remember is that you connect this kind of circuit to another circuit. You could for example connect V into some other circuit and you can measure VR. There are 2 things which you should remember, that this transfer function which you have here depends on what you connect at VR. So, if VR is perfectly an open circuit, means nothing more is connected here, this is the transfer function which you get, what I have shown you here, the frequency response. If you connect something at VR, then of course you are kind of loading this filter, and loading a filter actually changes its transfer function. So, that is an important thing, that if you load it very little, this is the transfer function, but the transfer function may get altered in case you load it. Similarly, this filter when connected to some other part of the circuit may load that circuit. Okay. If it is just the source, then it is loading the source. So, sometimes of course, the source also has got a source impedance. So, that also alters the overall transfer function which you may get. If you are measuring of course V in right where I have shown it, then of course the transfer function will not get altered, but if V in is not ideal and you in addition to V in you have got something in series with it, then the transfer function will get altered. So, just remember this interesting point, which can you come to the next? Now, one of the things I mentioned to you is the use of these kind of circuits in signal processing or even in power engineering circuits, where we can actually filter out, you can actually remove certain frequency components from a signal depending on the gain and gain which you have in the frequency response. So, if your gain is low, that component of at a certain frequency, then that component of the frequency gets attenuated. So, if your input actually has got a certain set of frequency, the output also will have those set of frequencies, but the scalings will be different. With the high frequency for example gets scaled significantly, then you would call it a low pass filter, I mean or high frequencies get scaled, then you get low pass filter. What is high and low of course depends on the cutoff or the 3 decibel or the bandwidth of that filter. Okay. So, for example, one of the ways of remember that when you are talking of filtering of signals, remember that if you have got a periodic signal, in fact all the analysis here which I have shown you applies to inputs of the form e raised to st plus alpha. So, S has to be so you are talking of periodic sinusoidal signals or combination of sinusoids or exponentially decaying signals or DC signals. In this case the input and output wave shape in steady state is the same. Okay. So, for those set of signals this filtering etc. makes a lot of sense. So, if you have got a signal which is periodic, let us say a square wave. Okay. A square wave in fact can be written down as you have done the Fourier series analysis, and for example, if you have got a square wave which starts at it has a wave shape which is shown here. In fact, it starts at t is equal to 0. I mean it has a value of 1 at t is equal to 0. It jumps from 0 to 1 at t is equal to 0, and it is symmetric, has a period here of which is 0.02 seconds, which is 20 milliseconds. This is a 50 hertz square wave, and in case you in fact you can represent this square wave as actually an infinite series of sinusoids. So, a periodic wave in fact can be represented as a series of sinusoids, and as we have seen before, if you have got superposition of sinusoidal inputs, which in fact this wave can be considered to be, then you in fact have got similar terms, similar frequencies in the response as well, although different frequencies get attenuated or scaled to different extents depending on the nature of the filter, okay, or the nature of the transfer function. I of course have been talking of low pass filtering, but you can also have high pass filters, etc. You can try some practice problems in which you have got different frequency behavior. Now, of course, there are of course some interesting points when you talk of a square wave. This this infinite series converges well, except at the point where there is a jump. So, in fact, this is called the Gibbs phenomenon, where you can by adding more and more terms to the Fourier series. Can you show the Fourier series? 1 to infinity, you can in fact try to come closer and closer to the wave, but actually at the point of jump it does not converge well. In fact, there is a kind of a oscillation which is called Gibbs phenomenon. This happens when you have got discontinuities in the periodic wave. This is an example of a periodic wave in which there is a discontinuity. Okay. One important point is, since it is a symmetrical square wave, in this particular case DC, there is no DC or average component. So, that is something which you can easily see if you have got if you take out the Fourier component. So, if you take a square wave, this is what you get, and in fact, because you have the square wave starting I mean the jump of 0 to 1 occurs at t is equal to 0, you have only sinusoidal components and no cosinusoidal components, but in general you could have sinusoidal and cosinusoidal components. And the other thing is because it is a symmetrical square wave, that is the first the top half and the bottom half look there is half wave symmetry, you will find that there are only odd harmonics in this. Okay. So, this is what is known as a Fourier series. This is just to correlate what you have done already in your undergraduate mathematics course. So, any in fact periodic wave you can consider to be a sum of DC plus a set of harmonic sinusoids. Okay. And of course, these sum of sinusoids all occur at multiples of the fundamental period, which is in fact 20 milliseconds in this case. Can you just indicate this? Yeah, it is a 50 hertz wave, so it is a 20. Okay. What you are seeing here is a reconstruction if you look at the left hand side figure, is a reconstruction for 100 terms. Okay. So, in fact, you can, this is an infinite series, but you only evaluated it till 100, and what I have shown you on that expression is what you get in case you apply the theoretical if you try to get the Fourier series components by the formula which you have learnt in your undergraduate course, that is in a mathematics course on Fourier series. Yeah. A similar thing happens when you got a triangular periodic wave. Now, the reason why I am showing you these waves is of course, the nature of the Fourier components changes. In this case, you will find that the Fourier coefficient is quite a little bit different from what you have in the square wave case. Okay. Here again I have chosen my time t is equal to 0 in such a way that I have got only sinusoidal components, but remember that the Fourier series can have in general sinusoidal and cosinusoidal components. If I choose my time t is equal to 0 somewhere else, keep the waveform as it is, but I shift my time axis, the Fourier series will have cosine components as well. Okay. Yeah. Similarly, I have got a sawtooth. In this case, if you look at the nature of the sawtooth, you will find that in fact VDC here is 0 because it is a symmetrical sawtooth, and in fact all the waveforms I have shown here so far are having VDC equal to 0, but in this sawtooth waveform you will find that you have got a, because I have chosen my time t is equal to 0 at the peak of that sawtooth, it turns out that there are only cosinusoidal terms. In general, you could of course shift the time axis and get different kind of terms, okay, cosine as well as sinusoidal. Now, suppose I take this RL circuit and design it with just have this R and L value as shown. We have got this transfer function between VR and VI, I mentioned this some time ago for this RL circuit, and for this RL circuit the transfer function between VR and VI is R upon R plus SL. So, that is the we are looking at the measured value is the voltage across the resistance and the input is the voltage across the RL circuit. So, your transfer function is R upon R plus SL, and you see that the cutoff frequency I have chosen is to be 100 hertz, 100 radians per second, I am sorry, 100 radian per second is in fact 100 will imply 100 divided by 2 pi hertz. So, if you go back, go to this frequency response again, if I give a input something like this, okay, what you will see is that this input is a sinus is consisting of two sinusoids, okay, of different magnitudes and different frequencies, and what we can do is in fact if you look at the cutoff frequency of the cutoff frequency is that place where that the curve kind of is 3 dB point is in fact 100 radian per second, which is around 31 hertz. So, 100 divided by 6 roughly is sorry, I am sorry, the cutoff frequency of the filter is of course or rather the 3 decibel bandwidth point is 100 radian per second, and what we have taken is the sinusoid of 100 sin omega ct, where the input is having a frequencies of 31 radian per second and 31 into 1000 31 into 100 radian per second. So, we have got two frequencies, one is high and one is low. You can see the low frequency is a very very benign and slow moving sinusoid, and riding on it is of course the high frequency sinusoid. If you actually pass this through the filter which I mentioned some time ago, so actually if you plot this on the log scale, you will find that this 31.42, this is the first term of that the two sinusoids, the first frequency is 31.42, that is hardly attenuated, your gain is 0 decibel, that is 1, and but at 3142 radian per second, which is the second term in the input, the gain is minus 30 dB, which is actually a very low gain. So, you will find that what we expect is that if I pass this input through the filter, you will have in sinusoidal steady state, this filter will block this high frequency component because it is a low pass filter. Yeah, can you go there? So, if I give an input to this and if you filter it, you will find that the output is the black, VR is the black thing. In fact, if you look closely, the VR hardly contains, in fact, there is a high level of attenuation of the high frequency. You do see a very small ripple riding on that black waveform, and that is the attenuated component of the high frequency component of the input, and this is of course in sinusoidal steady state. There is in fact also you will notice that at 31 the low frequency signal is slightly phase shifted, there is a phase lag. You will see the peak of the black signal slightly different from the peak of the blue signal, because the low frequency also gets phase shifted. So, how much is the phase shift? Can we go up there to the yeah, of course, we did not plot what this phase shift is, but if you look at the phase angle plot, which is not shown here in fact, you will find that there is a kind of small phase shift. Yeah, you see that there is a phase shift, In fact, near about this point you will find around 5-10 degree phase shift, which is also seen there, but we kind of missed out showing you the phase plot there, but you can a similar figure by looking at the similar situation here, you can see that you have got a phase shift, you can get in fact a phase shift. Okay. That of course depends on the frequency. If you look at, go back to that where we were. So there is going to be a phase shift around 31.42, which is not of course shown here, but you can imagine or you can plot it and just try to confirm this. Yeah. We will first go to the program. What I have done is actually done a simple RL simulation. So we will just show the simulation first. So what we are going to do is simulate this RL circuit, and what we are going to do is plot the current and voltage. Are we going to do that? Yeah. So what I am going to do is get plot VR and V input and look at the kind of responses we will get. Remember, VR is the voltage across the resistance in the series RLC circuit. So can we run this? And of course, one of the important things is the input we are going to give has got, could you mark it on the figure there? Yeah. So you have got 25 highlighted there, yeah, there is 25 hertz, 40 hertz and 100 hertz. So what I am going to do is give this 3 frequencies in the input, and what the magnitudes of them are 10, 5 and 2, and what I am going to do is numerically integrate. So I am not going to analytically get the transfer function, numerically integrate in order to get the output, and in order to do that I have actually used Euler method, which we have considered before. It is a simple Scilab program which you should try out for various other circuits as well. Can we run the program? Yeah. So what I am going to do is plot the input and output. So if you look at the input and output, this looks strange actually. So why does it look strange? Well, the reason it looks strange is of course is that the 3 frequencies are 40, 25, 40 and 100, and so if you can we plot this once the steady state? What is the time constant of this circuit? The time constant of the circuit is L by R. Can we look at what the L by R is of this circuit? L by R, yeah, it is 0.01. So we expect that this is reached steady state. The important thing is that if you look at the periodicity of this, you will find that if you have 25 hertz, 40 hertz and 100 hertz components, the periodicity is in fact 5 hertz. So you will see that this waveform keeps repeating here. Can you just show the peak of that highest peak there? Yeah, this one, and then it again gets repeated there. Okay, so you will find that this keeps on repeating, although the waveform looks very unhappy kind of waveform. The reason is of course that it contains 3 frequencies which are not integral which are not I mean 25 hertz, 40 hertz and 100 hertz are not multiples of each other. So the period is in fact 5 hertz of this composite signal. Okay, and but the point is of course that different frequency components you will find are attenuated to different extents. The input is given by the red signal and the output is the blue signal, and you can see that the blue signal has slightly lesser variation compared to the red signal, because the 100 hertz component is getting in fact to some extent attenuated. Okay. So in fact if I take L by R to be some other value, for example, can you just make it the L much larger? Maybe if you make this L 100, so I have increased the time constant. Now I have increased the time constant, the cutoff frequency is in fact got lowered, and now you will find that if I run this simulation, you will find that in fact the higher frequency components kind of go away, and the frequency component which remains is going to be, can you just show the frequency component which remains? The 25 hertz and the 40 hertz component are the ones which will remain. The 100 hertz component kind of goes away, and there is a significant attenuation at the 25 hertz and as well. Okay. So this is a composite signal with a frequency the frequency, since it has 25, 40 and 100 hertz components, the periodicity is in fact 5 hertz. Yeah. Remember that right in the beginning there is of course a natural transient. Okay. So, this natural transient is there as we can expect it to be. So, you can notice that there is a slight DC offset initially in the blue waveform and that decays. So, you still have this e raised to minus r by ALT right in the beginning when you switch on this circuit. That is an interesting point which you should always remember, that you do have a natural transient, it dies down and eventually the input and output wave shapes have the same frequency components as the input. Now, what it also means is that if you got a linear circuit, you can actually get its frequency response by actually exciting it with various frequencies. In fact, how do I get this frequency response? Can you just show that? One of the ways to do it is if you show the slides. Yeah. So, how do you get this phase? And one is of course trying to do it analytically as we have done, but in case you have got a black box and you want to actually take out this frequency response, then what you should do, what you can do is excite this input at one frequency, see the gain and the phase shift which occurs at that frequency, and you can do this one by one. That is, you can give an input at for example, here at 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz, one by one, and get the output. Okay. But remember that in each case you will have to wait for the natural response to die out and then take out the gain and the phase shift. So, if you want to do this experimentally, one of the ways of doing it is to inject sinusoids of different frequencies one at a time and wait in each case for the natural transient to die down. There will be a natural transient here as well, and then once the natural transient dies down, you see the gain and the gain scaling which has occurred between VR and Vin, and also the phase shift between VR and Vin, and then you plot this for different frequencies. Okay. So, this is one way to get the frequency response of say a black box experimentally. But in case you want to, but one thing I mentioned to you that as we saw in the simulation here, if you give a mixture of frequencies, the output also will contain those frequencies because it is a linear circuit. So, the output in steady state will also contain. So, actually Vin can not contain one frequency, you need not do this one frequency at a time. If you do it one frequency at a time, for every frequency you will have to wait for the natural transient to die down and then do the measurement. Instead, what you can do is you can make a Vin a composite signal consisting of many frequencies. Just in one shot you can give the input to this circuit, wait for the natural transient to die down, and then you measure VR. The VR will have also the frequency components corresponding to Vin, and there is a one-to-one correspondence between the response at a particular frequency and the input at a particular frequency. So, so you really do not have to do this kind of exercise one at a time. You could actually inject many frequencies at a given point and in fact get the response. Like in the example I showed you, we injected 25 hertz, 40 hertz, 100 hertz, but you could really put a large number of frequencies and get the output. And of course, thereafter we are what we need to do is obtain the Fourier series components of, if it is a periodic waveform. In the case shown here, in fact the period was 5 hertz of that composite signal. So, you take the periodic the Fourier series components of the input and the Fourier series components of the output. For every frequency then based on the Fourier series of the input and the output, you can actually get the frequency response. Okay. So, this is what we can actually do. One, for example, just to give you a visual feel of a signal which has got many frequencies. This is an example. This is in fact a signal which is periodic, but it has got many frequencies. So, in fact this is a signal which is having a period of 0.01 a period of 100 seconds, that is 0.01 hertz is the kind of frequency we have, but in fact it contains the frequencies 0.01, 0.02 and so on to fairly high frequency. So, you have got actually I can excite the linear circuit this kind of multi-sign signal and in fact obtain the response, and thereafter take the Fourier series of this signal and also the Fourier signal series of the output signal and get the frequency response. So, for example, but of course, if I in this particular multi-sign, all the sine waves are not having the same phase. In fact, they are different phases. So, you get a signal which has got a limited magnitude. Otherwise, if you try to add up a large number of multi-signs, the overall magnitude of your signal can become quite large. Okay. So, if you have got 100 multi-signs and all of them for example, are sine waves, you will find in fact that the kind of signal you will get is what is going to be shown in the next slide, like this, which is almost this is 10 raised to minus 3 into 10 raised to minus 3, yeah, come to the previous one, whereas this is 2 into 10 raised to minus 4. Both these signals have the same frequencies components, but what I have done in this particular frequencies, this particular signal is added up sine waves, but all the sine waves are not having the same phase. Okay. So, in that case the summation comes out to be of a lower magnitude, whereas if you look at the next signal, all the signals are in fact sine waves and they have got exactly the same phase, but they have got different frequencies. So, then the summation comes out to be a peaky kind of signal. So, you have got a very large amplitude signal. So, if you want to avoid that, which is useful in some situations, you will find that it may be a better to give a multi-sign with the same frequency components, but the phase angle of the individual sine waves is chosen in such a way that we optimize and make the overall magnitude less. This is useful in case you are doing some kind of experiments while the circuit is in operation. You are kind of disturbing it using this probing signal and you are trying to take out the transfer function of the circuit while the circuit is working. So, in that case you will inject a small like probing signal and it is important to keep it small. So, in that case this kind of probing signal is useful. Let us go back to the circuit. We will not take a this kind of signal right now, we will just take a simple multi-sign in our simulation and try to redo this. So, in our multi-sign we just take 3 signs. What is the 3 signs? 25 hertz, 40 hertz and 100 hertz as shown in the program here. And well, since we are giving the input, it is not very difficult to, in this case I have used sine, all the 3 as sines, but it was not necessary to have them all having the phase and phase, you could have made it sine 2 pi into 25t plus something. It is not important, you could have made this plus 30 or 20 and so on and redone this simulation. The corresponding output corresponding to this 25 hertz also would have got phase shifted in the sinusoidal steady state. So, if I use this multi-sign and give it to this this circuit, and we have already seen the output, but the Fourier series components we already know. What are the Fourier series components? Can you go up? For example, there is no DC component, there is a 25 hertz component of magnitude 10, there is a 40 hertz component of magnitude 5, can you highlight that 5, and there is a 100 hertz component of magnitude 2, and the output on the other hand, we do not know the output, we could analytically actually get the components of the output because we know the transfer function, but if we do not know the transfer function and this is a black box, what we would need to do is take this VR, which is RL into I, R into IL, and obtain the Fourier. So, how can you obtain it? Well, you know how to obtain Fourier series components, but you have done this in your undergraduate course on math, but I have just recomputed it here. Yeah, what you need to do of course is if you want to take out the Fourier series of a signal, what you need to take is isolate one periodic signal or one period of the sinusoidal steady state. So, what you need to do is take a window of 5 hertz. So, he is showing it using the arrow. This can you just show it using yeah. So, this portion, okay. You take one period, one fundamental period. In this case, since it is 25 hertz, 40 hertz and 100 hertz, the fundamental period is in fact 5 hertz, okay. of this signal, composite signal. So, you take the output signal and try to obtain the output signal is blue, you obtain the Fourier components of this. Now, Fourier components consists of DC. In this case, there is no DC. Remember that we have excluded the natural transient. So, the natural transient has died down, and what you have is a periodic steady state of 5 hertz. So, take a 5 hertz, that is 1 upon 5 hertz, that is 0.25 second, 0.2 second window of this waveform, and actually do the integration of this waveform using the Fourier integral. But remember, the Fourier series integral is in fact a steady state, kind of a continuous time integral. So, if you look at the formula, if you look at the Fourier integral, it is in fact, suppose I give you a a square wave, suppose. So, how do you actually compute the Fourier series components? You, if this is f of t, this is t, then you have to integrate over a cycle, over one cycle, this is one cycle. Once it has reached periodic steady state, this is a steady state waveform. Remember, you have to exclude the natural transient, which dies down after some time, and then take f of t multiplied by e raised to j omega t into k into d omega dt, and then divided by t. So, this will actually give you two components. One will be the coefficient of the sine and one is the cosine coefficient. So, when you did your undergraduate course on math, you may have actually done this integration with sine and cosine, but you can in fact do it in a composite way by simply taking e raised to j omega t, which is actually cos omega t minus j sin omega t. So, you can do this in one go with a complex integral, then separate out the real and imaginary parts and get the coefficients. Okay. So, of course, this is a continuous time integral, but what we have in fact in the numerical integration are discrete values, and because this is what we have got, we in fact do this in discrete time. So, this is called a discrete discrete Fourier transform. What we do is we take this waveform only over a discrete samples of the waveform over one period of this waveform. So, this program here, so actually this a minor correction here, this, since we are talking about the nth coefficient, we will put n, omega into n into t. Okay. So, of course, this has to be done as I mentioned using samples, discrete samples. So, we actually approximate this integral by a summation. Okay. So, instead of doing ft, this is a continuous time integral. So, what we do is take one period of this waveform and we actually evaluate, this program will be made available to you. So, you can actually evaluate this using the formula which is shown here. This is actually we evaluate in the discrete, using discrete samples, we evaluate this integral. The integral becomes a summation over one period. Okay. So, once it reaches steady state, we actually get the Fourier components. Remember, we are doing this numerically. In this simple circuit, the transfer function is r upon r plus SL. So, it really does not take much to find out what the gain and the phase is analytically. I can just plug in the values of omega is equal to 2 pi into 40 hertz, 2 pi into 25 hertz and 2 pi into 100 hertz, which are the three components, and get the individual magnitudes and phase shifts. But I am showing you how one can do it numerically. Okay. This is actually required when we actually do not know what the transfer function is in the analytical form, which is often the case in many practical applications. So, this is actually computing the various Fourier components. In fact, this computation of Fourier components is required later on in various algorithms related to electrical supply systems, like measuring the RMS value of a waveform, computing the apparent impedance seen by a protective relay in a transmission line, and therefore, you can use these kind of you need to actually extract the frequency components of the system. Okay. So, this is showing you how we can take the input and the output, we can take out the Fourier components. Once you take out the input and output Fourier components, we can actually obtain the magnitude and the gain. Remember that the an and bn coefficients, if you take square root of an square plus bn square, that will give you the magnitude of the response, and tan inverse bn by an will give you the phase response. Okay. The same thing you can do for the input and output, and then take the ratio. In that case, you will get a transfer function. So, in fact, that is what is shown here in this program. You can see what is given there, and then it can be plotted. Okay. Now, this is over a large number of samples, because we have taken h is equal to 10 microseconds. So, the really large number of samples. Such a large number of samples is probably not required if you are having waveforms of 10 hertz, 100 hertz, 25 hertz and 40 hertz, and time constants which are only 0.1 seconds or 0.01 seconds. But we have probably been a bit inefficient by considering such a small integration time step. So, we have actually got a lot of samples. In fact, we can downsample it, because we know that this does not, this way these the responses do not contain very high frequency components. So, we can actually downsample it. This is not done here, but there are various ways to improve the efficiency of the program which you can think of. Okay. So, if all these things if you are going to do in real life, you can try to optimize on the computation time, etc., and choose appropriate values of h, the number of samples and so on, when you are trying to approximately compute the Fourier components. So, this is not a very efficient way of writing a program, efficient implementation of computation of this Fourier component, because the number of samples, as I said, is much larger than required, and so we will just directly show you the output. So, actually you will notice that we will have to just first show it, yeah. So, in fact, this is it has got, you will find that the input is blue. The Fourier series of the input have components at 25 hertz, 40 hertz and 100 hertz. Actually, this is the program has actually interpolated these points. Actually, there are only discrete points at 25 hertz, 40 hertz and 100 hertz. Okay. So, it is 0 elsewhere. So, actually that is why you are getting a kind of a jump there, but actually there is only one point here. So, it is done a linear interpolation between 20 and 25. If you look at green, you will notice that the Fourier inputs, rather the components are much lower. That shows that this is actually attenuating the signal at at both 25, 40 as well as 100. In fact, the 100 hertz component is hardly visible here, it is just a small bump there. So, the output also has exactly these frequencies. So, you can actually take out the transfer function by simply by taking the ratio of the input and output at these frequencies. Okay. In fact, since I have used complex numbers, in fact, I have used complex numbers to indirectly get the Fourier components, not sines and cosines, which are real signals. What you see here is that you will get exactly symmetrical values about 0. Okay. So, if this is 0 hertz, you get a component at minus 25, minus 40 and 100 hertz as well. Okay. Now, if I change the time constant of this, of course, you will find that the the ratio of the input and output will change. So, the important takeaway is that you can get the transfer function at these frequencies by taking the ratio of the input and output at these frequencies. And how do you get the input and output at these frequencies? You can actually numerically get the Fourier series components. If you know it analytically, of course, you do not have to do all this, you can actually get it analytically as well. The phase components also can be obtained in a similar fashion. It does not look very pretty here, but because it is interpolated. actually there are no components in between 50, 40, 25 and 100 hertz. So, you should only see the values at 40, 25 and 100 hertz. This program here has interpolated in between, and that is why you are getting values in between as well. But this needs to be you remember that when you are plotting these things, there are discrete frequencies. So, really you should not interpolate between the points, there is no reason for doing it. This is not how it should be actually depicted. Okay. So, now just imagine what would happen in case I injected the multi-sign. In case of the multi-sign which I showed you some time back, the multi-sign composite multi-sign in this, if I injected a signal like this into the system, then you have got so many frequencies. So, you will actually get almost at a large range of frequencies, and you can actually mimic the complete Fourier response, or the Fourier the complete transfer function. Okay. Here I showed 3 frequencies, 25 hertz, 40 hertz and 100 hertz. Is that okay? So, in fact, you can obtain the Fourier series components in this fashion in a discrete domain. I encourage you to actually look at the program and just try to do things. What has been done in the program is a large number of samples have been taken, and we have in fact obtained the Fourier series components one by one. In fact, if you have got a huge kind of range of frequencies, in this case, for example, in the multi-sign shown here, we have got frequencies 0.01 hertz, 0.02 hertz, right up to relatively high frequency. In fact, you can use some efficient algorithms. One of such an algorithm is the fast Fourier transform. I will not be teaching it in this course, but I wanted to show you the place of these things. If you try to run the program which is shown earlier, it is not efficient. In fact, you can gain a lot of efficiency if you use certain certain algorithms, and I encourage you to explore what this fast Fourier transform is. It is an algorithm to obtain the discrete Fourier transform. Okay. A discrete Fourier transform is an approximation in the discrete time domain of the original Fourier series algorithm, okay, which is in fact a integral. Okay. So, this way you can actually obtain these frequency responses, and the whole objective of this exercise is actually to make the connections between what you have learned in maths, numerical analysis, where it actually finds use in our circuits and power systems is this. Okay. So, we shall see later when we later when we talk of protection systems, we will be actually using, we will need to actually extract from the waveforms which are measured all these especially the Fourier fundamental Fourier series component, and many of the algorithms are in fact based on this kind of frequency components of the signals which are measured. Many of the protection algorithms, protection I mean how to detect that a fault has taken place in a certain region. So, you need to actually do some signal processing to in fact infer that. So, this kind of thing is used quite frequently, although we are power engineers, we will actually see that signal processing is an important thing we need to learn as power system engineers. So, we will stop here.